Hi everyone. In this video, we'll be talking about the arc length and the parametrization using arc length. Let's begin with the arc length. Suppose a vector-valued function R with components x, y, and z traces out its graph exactly once on the interval from a to b. Then the arc length of this graph is given by an integral, the integral from a to b of the square root of the sums of the derivatives of R's components squared. An easier way to remember this is as the integral from a to b of the magnitude of R prime. Let's move on to arc length parametrization. Given a vector-valued function R, its arc length parametrization with initial point R of t naught is given by R star of s equals R of t, where s and t are related by the equation s equals this integral, the integral from t naught to t of the magnitude of R prime. Now, in this case, s is called the arc length parameter and t is the original parameter. How would we calculate an arc length parameterization in practice? Well, first we need to calculate t naught because this gives us the initial point, which is R of t naught. After that, we need to calculate the equation relating the arc length parameter and the original parameter. In this case, we'd have to evaluate this integral with the bounds t naught and t. And if you evaluate this, you'll get some expression in terms of t. Okay, so after that, we solve for t in terms of s. Let me write that down. We solve for t in terms of s. So let's say t is equal to 5s. And using this, we obtain R star of s equals R of t equals R of 5s. All right, so we just plug in the function of s. So in simple terms, R star of s has the same graph of R. But what's special is that R star of s refers to the point s units along the graph from this initial point, R of t naught. So this means that s tells you how far you are along the curve from this initial point. So here the value of the positive direction is in the direction of increasing parameter values. Okay, how about curvature? The curvature kappa t of a space curve R is given by any of the following equivalent expressions. The first is the magnitude of the unit tangent vector, which is differentiated with respect to the arc length parameter. So in this case, you'd have to parameterize t by arc length first before taking the derivative and then the magnitude. But if you don't want to bother with arc lengths, you can just use this formula, which is the magnitude of t prime over the magnitude of r prime. Alternatively, you can skip calculating for the unit tangent vector t and just use this formula, which is in terms of the derivatives of r and magnitudes of those derivatives. So the radius of the curvature, on the other hand, is given by rho of t, which is equal to 1 over kappa of t. Now, the curvature measures how much a curve deviates from being straight, while on the other hand, the radius of curvature gives the radius of a circle that best approximates the curve at a point. Let's move on to some problems. So let's solve for the following. Find the arc length parameterization of the vector valued function R, which has these components. And find this for t greater than or equal to 1 using the arc length from this initial point. For the solution, we first note that this initial point is given by r of 1. So if you go back to the definition of the arc length parametrization, you would say that t naught is equal to 1, because this is the input value which gives us the initial point. Furthermore, we need the derivative of r, because we'll use this to get the equation linking s and t. So the derivative, as you can check, is this function. We also need the magnitude of the derivative. So this is a straightforward setup. We square each component and you add them. And by simplifying, we get the derivative, the magnitude of r prime is equal to t squared. Okay, so using this, we can calculate the relationship of s and t. So s is equal to the integral from 1 to t. We have 1 here because this is equal to t naught. So we integrate the magnitude of r prime of u du. So again, we calculated this to be u squared. So we substitute that in, we calculate the integral, and we plug in the bounds of the integration. We get this formula. Now we solve for t in terms of s. This is a straightforward manipulation. You can multiply by 3, you add 1, and then you take the cube root. Okay, so now we have t in terms of s. We can plug this into r of t. And if we do this, we can obtain r star of s. So again, r star of s is equal to r of t, and t is equal to the cube root of 3s plus 1. And we simply plug in this expression into the definition of r, and all in all, we get this function. Next, we are asked to find the coordinates of the point located 7/3 units along the curve from 0, -1/2, 1/3. Assume that the positive direction is in the direction of increasing parameter values. For this problem, we note that the required point is r star of 7/3, where r star was the arc length parameterization we calculated earlier. Why is this? Well, by definition, r star of 7/3 is the point located 7/3 units along the curve from the initial point. And the initial point given in the previous problem was 0, -1/2, 1/3. So all in all, we know that this is the point that we're looking for. So to calculate for this point, we note that this is equal to r of the cube root of 3 times 7/3 plus 1. This comes from the previous equality of r star of s equals r of t, which is then equal to r of cube root of 3s plus 1. So we invoke this for s equals 7/3. We get this. Okay, so this inner input simplifies to 2. And we just need to evaluate r at 2. You should get this vector. So that's it for this question. Let's move on to question 2. A curve known as the Euler spiral, this is pronounced Euler, not Euler, is parameterized by the vector function r equals the integrals of some functions. Now we have to verify that R is parameterized by arc length from the origin. First, let me comment on this, that R is a function of t, and over here, the components are also functions of t. It might be a bit hard to see that, but for example, if t were equal to 1, then R of 1 would be equal to the integral from 0 to 1 of sine u squared over 2 du, and similarly for the other component. And this is actually just a number. It's an integral of a function, so that simplifies to a number. So this is actually just a function of t. The t just shows up as the bound of the integration here. Okay, so for the solution, what we can do is we can show that the given parameter t is the same as the arc length parameter s with respect to the origin, which is r of 0. And to do this, we can first use the first fundamental theorem of calculus to calculate r prime. Now, the first fundamental theorem of calculus, this is a theorem that says that d over dt of t a f of u du is just equal to f of t, where a can be any number. So you can reflect on this for a while and see how it applies in this situation. And if you apply it, you'd actually get that r prime of t is equal to this one. Okay, next, we take the magnitude of this one, of r prime. And this is easy to simplify because this is sine squared plus cosine squared. And this, by trigonometry, this simplifies to 1. Okay, next we can find the relationship of s and t. To do this, we say that s is equal to integral from 0 to t of magnitude of r prime. We take the integral and get that s is equal to t. And this is what we wanted. It tells us that the arc length parameter is equal to the original parameter. So in the first place, r of t was already parameterized by arc length. Okay, let's move on to the second sub-question, which is to calculate the curvature of the Euler spiral. Now, since the magnitude of r prime is equal to 1, as we calculated earlier, the convenient curvature formula to use in this case would be kappa of t equals this fraction. In this case, we don't have to worry about this denominator because it's just equal to 1. So in order to calculate this, we still need this numerator. So we begin by calculating t. This is the unit tangent vector. And the unit tangent vector, if you recall, is defined by this formula. So we previously calculated r prime. We get this expression. We take the derivative of the unit tangent vector. And to do this, we simply apply the chain rule. You can check that we get this expression. Okay, finally, we can compute the curvature. Again, it's defined by this formula. And since magnitude of r prime is 1, we ignore it. And we simply get the magnitude of the unit tangent vector prime, t prime. So getting the magnitude, we can simplify. And we note again that this can be simplified as t squared cosine squared of something plus sine squared of something and this is just equal to 1. So all in all, we get the square root of t squared, which is equal to the absolute value of t. So that's the curvature of the Euler spiral. And you can search in the internet actually for a picture of the Euler spiral, and you can try to observe how this curvature makes sense. Okay, that's all for this video. Thank you for listening.